were this slide. The cosmic background radiation is also known as the cosmic microwave background radiation. The work of Penzias and Wilson during 1950s has fetched the Nobel Prize in 1970. A remarkable evidence for the observation of the early universe or the observable. How far we can see that we can see it depending upon our eyes. If you see through the telescopes, you can see further. If you still see through some kind of an antennas under then magnifications, you can go to some extent of it. And what it says is that in such a way, how far we can see that, how far we can see the radiation which is coming from the longest. Assume that if you're seeing sun means the radiation emitted by the sun can be seen. Means sun is at about 150 million kilometer. Will have the signatures of, will have the properties of how that sun is made of, how that sun is working, or how that sun is behaving, or if instead of sun, you can call it as a star. If you know the characteristic features of its properties, both preferably physical, then we can also having a capability to study any other kind of a stars. Assume that if you know 10 minutes is the time required for the radiation coming from the sun, then we can analyze that how that by analyzing the radiation, which is what we are receiving actually, we can say that what must be its energy, what must be its temperature, what must be its wavelength, what it is made of actually, when it was made of, how it was made of, some kind of speculations, and then maybe we can develop a theory. Like that, if you go for billions of years, the same thing can happen actually. In fact, the discovery of cosmic background radiation gave the very much ideas of the existence of the universe, how it was formed in the beginning about 13 years ago. This is what I've shown actually. Uh, yeah, what its significance? It can say that significance of CMB radiation, in the sense significance of studying the cosmic microwave radiation, is that CMB radiation was emitted 13.7 billion years ago, only a few 100,000 years after the Big Bang. I will come back to this slide. Okay, a few 100 years after the Big Bang actually. Means by studying detailed physical properties of radiation, we can learn about the conditions that prevailed in universe on enormous scales at very early times, because the CMB radiation was the one we see today, which has traveled over such a large distance since then. Make use of these things. Looks like number of slides may be more. The content, why it is relevant for you, you can answer to the queries or the questions either in the exam or wherever you go on cosmic microwave wave. CMB is at a uniform temperature with only small fluctuations, varying by not more than 1 part in 10,000. Means 1 over 10,000 times 100 you can mark, about roughly 0.01% is the variability or variations. These fluctuations are visible only with very precise telescopes. Means to say, a knowledge of these fluctuations is very much essential for us, and this knowledge enables us or provides us the cosmologists, of course, us in the sense, us and cosmologists, to extract the information regarding galaxies' origin and large-scale structures of the galaxies. For instance, first spaceborne full sky map of CMB radiation was plotted by or obtained by NASA's Cosmic Background Explorer, that Cosmic CO, Cosmic Background Explorer COBE mission. I shown you one graph here, the COBE. This is in 1992, hardly 30 years, was obtained by the NASA, okay, Cosmic Background Explorer. This map came to be known as the baby picture of the universe. It confirmed the Big Bang theory of the expansion and the predictions, and showed hints of cosmic structures that were not seen before. And another detailed map came in 2003, Wilkinson Microwave Anisotropy Probe This picture revealed the universe's age to be about 13.7 billion years ago. I will go back. This is W map. Okay. These three gave in such a way, see that here to here, we are having a lot of informations at finer scale actually. It gave that the universe was began around 13.7 billion years ago. The last one with last in that picture, it also revealed, it also revealed here that anisotropy, you can see that anisotropy probe in the sense, see, wherever you go, it is not, it is of the uniform case, either left or right, actually, you can see entire thing actually. There may be some kind of an anisotropic property in such a way, center part of the universe, middle part of the universe, maybe at the edge of the universe. Edge of the universe is known as the observable universe. This is the edge. This is the observable universe. Beyond this limit, wherever the white patches are not patches, white background is there, that we can't see actually here. Not for this, for entire thing actually. Observable means up to what extent you can see. It also revealed that oldest stars started shining about 200 million years after the Big Bang. In the sense, the stars were not formed earlier, they started after 200 million years after the Big Bang, far earlier than they predicted actually. Here, if you go here, this is a first flat 400 million. They told that it is 400, 200 billion years actually, far ahead of the early beginning. 200 means somewhere here it mentioned like the 200. Of course, 200 million somewhere here. This is 400, no? Somewhere here. Dark ages where it started. They expected that the first star has formed after cooling and it coalescence happened. Because of the coalescence, the atom formation of the atoms has happened in such a way with central part of a nuclei and the electrons revolving around the nuclei as a first single hydrogen atom. Then a group of hydrogen atoms, maybe an helium, maybe a carbon, maybe a neon, maybe a nickel, maybe a gold, maybe iron, maybe cobalt, whatever may the elements you remember in your periodic table, they are all the known elements. Unknown, there will be something else. That is the main criteria why space astronomy, sorry, space agencies are putting efforts to go to the other celestial bodies. The nearest celestial body is natural satellite, moon, maybe the nearest planet, either Mars or Venus, we can go. Mars, we already tried. Venus, still there is a mission. I'm good enough to make you in such a way that yesterday you might have witnessed the panel discussion which was happening for the Aditya mission. Out of 8 fellows, I know personally 6 members. In the sense, not for knowing that what things are going on, but how the things can work it out actually. Means being that we are also, Bangalore University is also part of in Chandrayaan 3. Bangalore University is also involved in Aditya 1 mission, and Bangalore University is also involved in the coming Venus mission, particularly for the science part of it. We are not part of a technology. We are not part of the rest of the part. We are part of the science. Means for discussions we will be there, for getting the ideas will be there, for sharing the ideas or from our opinion will be there. We can also make a comment on it. We can also make an we can also put our words actually for the implementation of mission or for the other. Certainly, we will put a proposal from Bangalore University for the Aditya to receive the data. Okay. Here, my intention is that just a listen actually. Uh, Here, somewhere here. This is about 200 billion years after the Big Bang, or earlier than the predicted. That doesn't matter. At present, it will happen of that kind. Then, with the advancement of that, but we can shine how that should be there. Yeah, when you saw earlier in the middle, which is a W map of that kind, actually, you may not be noticed that what the W map means. This was followed by another set of CMB data collected by the European Space Agency's Planck's Space Telescope. That is the third one. Third one, what you can expect, which showed the CMB's highest precision picture yet. Means this map also spotted a cold spot that was bigger than earlier expected. Cold spots, cold spots, cold spots, cold spots. Earlier, it was not of that kind actually. Okay. The CMB data has also hinted at the dark matter and dark energy that is mysteriously accelerating the expansion of the universe. Undoubtedly, means without no doubt, without any doubts, the cosmic microwave background is one of the most significant tools used by scientists to learn how the early universe was formed. and is definitely expected to reveal a lot more exciting stuff in the next to come. What happened here? The cosmic microwave background temperature fluctuations as measured by the WMAP, the colors representing a tiny temperatures here, okay, fluctuations. Red regions here, you can see that red somewhere here, some dots here, somewhere here, somewhere here, somewhere. This particularly in the equatorial region actually, regions are warmer and blue regions are colder by about 0.30 followed by 2 degree Kelvin. Okay, 0.30 degree Kelvin. All temperature measurements are there. This picture shows the map of CMB measured by the Wilkinson Microwave Anisotropy Probe, a space-based microwave telescope for studying this. By studying this map, astrophysicists have learned an enormous amount about the evolution and the composition of the universe. Means they came to know that how that universe was made up of composition of the universe and also the evolution, also the beginning of the a uh, beautiful observation and a beautiful record of the entire universe which was formed through the CMBs. Yeah. This is the one and most represented picture about the Big Bang expansion, about the universe, about the origin of the universe, about the past. Thanks to the NASA, particularly WMAP science team for providing this one. We have to give the credit for that. You can spend a work, you can have an assignment, you can have a dissertation part, you can have a project work, you can have a research or PhD on this and produce thousands of papers, hundreds of PhDs only by observing this phenomena. It's such a large information. It carries such a large information. The earlier picture, what is there? This is tilted left or right vertically. Okay, that is the case. See this. This is the one. This is the one what I shown actually. Due to the expansion, how it is expanding with reference to the time. The expansion happened from here as a cone. See that actually. Okay, not like a ice cream cone of that kind, such a steep thing. Being a cylindrical, maybe a cup, a glass, they can call a glass, beautiful glass, where the bottom has having some diameter. As you go to the top, the diameter of the top increases very slowly. This increasing diameter shows us the expansion of the universe. These different circles, what you are getting is the existence of the universe at any given amount of time. This was at the beginning, this was at the middle, this was later, this was later, this is 13.7 billion years, 7 billion years passed ever since the expansion phase. This W map is making observations. How it has to happen, you see that. Yeah, this is the first quantum fluctuations. What happens here? Here, when it first started, actually, we are not sure that what is going on. Okay, then this has happened. Afterglow means after 400,000 years, afterglow, light pattern appeared like this. Okay, and in between there is a dark region or dark edges for few. This picture, what you are expected, this is the first stars about 400 million years. This is 400 lakh. This is 400 million years. Means again multiplied by 1,000 years. From the beginning, 400 million years was the first. Okay. Then maybe the separation goes almost about this is the 400 roughly this 400 to 1,000 million years of that kind actually. The development of galaxies, development of planets, etc., took place as the time goes. This is the dark energy accelerated expansion. You can expect here actually how it is there. See this one, which is appearing in dark. It can be here, wherever you want to go, wherever you want to go, dark actually. Okay. This you translate with the earlier figure, what I wrote or what I mentioned here. See that this is the Big Bang has happened. This is the region. This is the dark ages. This is the point where the first what we expected. This is the position of the first stars, not star, first stars. Formation of the first stars. Formation of stars at the first time actually. This was it. Then the expansion took place. Due to the expansion, the temperature was coming down and down and down to an extent of 2.75 degree Kelvin. See that this is what it says, that this graphic shows the universe as it evolved from the Big Bang to now. This Goddard space scientists believe that the universe expanded from subatomic scale, like independent electron and independent proton, independent neutron, and mesons, muons, kaons, all independent elementary particles into an atom form scales to the astronomical level, to the extent of subatomic level, atom to an element, to a molecule, to a cluster of a molecule, to a cluster of molecule, to a bulk molecule, and like iron rod, then I maybe a nickel rod, mixture of different elements, maybe the composition of the clusters, then different compositions to the liquid form, then liquid to a gaseous form. As the density goes, because of the attraction to the formation of the planets, to the formation, we can't call them as the planets, we can call them as the huge celestial bodies, as the stars. The formation of the planets is having a different theory. I will let you know later. Astronomical, it a fraction of a second after, as that took so large time, fraction of a second after its birth. They now building along with the universe, the partners. Then this is NASA. NASA is building along with the different university partners an instrument that searches for the clues that the inflation did. Here, where this inflation, what you are expecting, inflation did in fact being this. How does detection can go? This is the detection of the weak background noise, hardly of the order of microwave. This is the oldest light in the universe. This is a NASA satellite as captured this picture in the sharpest even picture, the afterglow of the Big Bang. This was taken during 2001, something like that. The full sky map of the oldest light in the universe. Colors indicate warmer as the red here, the same case, cooler as the blue spots, wherever you expect. Blue spots are more. The oval shape is the projection to display the whole sky, similar to the way the globe of the earth can be represented. Well, the fact here, the description goes like this. The fact that the universe is expanding is one of the most profound discoveries of the 20th century. That is why we are learning under this umbrella the landmark experiments or landmark evidences of the 20th century in physics. This means that the universe was much smaller, where the universe was much denser, very much smaller, volume was very much dense, high dense, and very hotter in the distant past, about 13.7 billion years ago. Oh, it was highly dense, very small universe, and it was very hot at such high density and high temperature. Both density and temperature are high. The universe was in the plasma state. The matter and the radiation were in thermal equilibrium. That's matter and the radiation were in equilibrium. In the sense, if you bring them together and together, density increases. Increase in density holds the radiation together, or increasing in energy holds the radiation together along with increasing in radiation or increasing in the energy thermal energy in terms of the temperature or the high radiation holds the matter together, becoming a high dense. Radiation and the energy, both of them are high, holds the matter together by increasing the density. Or if the density increases, then that can be held due to the gravity to that extent. Nothing could coagulate, nothing could join to form even the atoms or molecules of when the universe started. Once this state has reached, that is the maximum limit of the coalition, maximum limit of the maximum density, then the universe started expanding. Both matter and radiation cooled. Both radiation cooled, both matter and radiation cooled means matter cooled by the emission of the radiation cooled further by the re-emission of the radiation to the space. Today, as predicted, the age of the universe is 13. Yeah, what a wonderful experiment. This is not a big thought, but After the initial 400,000 years, something amazing happened in the universe. This phenomena that occurred long back, but still it is continuing. Whatever it was happened at that time is still continuing and still continues to have its traces in the universe even today. That is cosmic background radiation. Means, for example, assume that today is the third day of September 2023. Assume that you are making measurement of 100 years back, 3rd September 20, instead of 1923, for example. Whatever which has happened on next day will be observed for tomorrow. Whatever will happen on 1 year later will be observed for 1 year later. Otherwise, maybe we can observe. It's not a time domain of that kind. Always we can go window. So something which is emitted long back can be detected in this dawn of time. Dawn of time. What is the dawn of time actually? See that here. This is done. The right side is the picture of 13.7 billion years ago, how it was there. This is about 380, 100, 380,000, actually, in fact, 400 what we made because of this inflation. This is the inflation which is happening here actually. Any fraction of a second it has happened, maybe formation of this star. This is one example. WMAP observed light which is emitted in the universe when the universe was about 13 plus billion years younger than it is today. These numbers here, what you are expecting, represent a milestone in how we view our universe. This is said by Dr. Anik Kenny of NASA Director for here. This is a true turning point for cosmology. The light we see today here, this one, as the cosmic microwave background, which has traveled about 13 billion years to reach us. We think this light are infinitesimal patterns that mark the seeds of here, that mark the seeds of what later grew into the clusters of galaxies and that vast amount of structures we see all around us. Patterns in the Big Bang afterglow were frozen in place only about 380,000 years ago after the Big Bang, a number nailed down by this latest observation. These patterns are tiny temperature differences within this extraordinary, evenly dispersed microwave, like which is taking a bath or bathing in the universe, which now averages to reach temperature of about 2.7 degrees above absolute temperature or 2.7 degree Kelvin. WMAP resolves the slight temperature fluctuations here, which vary by only millions of a day. Being this, what is the cosmic microwave background? If it looks like a repeat here, the thing is that after going through this, the CMB radiation has a temperature of about 2.7 degree Kelvin, and its spectrum is a thermal black body spectrum curve. Since the birth took place around 13.7 billion years ago, the universe is continuously expanding and also cooling. Both are happening simultaneously. After 400,000 years from the start of the universe, it cooled down to a temperature of about 3000 degree Kelvin. Here they have mentioned Celsius, doesn't matter for that. At this point, the simplest atoms formed in the universe and the matter decoupled from the radiation. The light from this time, Mr. 13,000 years, 13.7 billion years back, has been traveling through this space ever since. This is what uses the cosmic rays. The CMB radiation can be detected all around us from here on Earth or in the space. It's like we can measure the afterglow of the Big Bang. Instead of seeing the afterglow at 3000 degrees, today we see this at about minus 270 or 3 degree Kelvin. This is due to the reason that the universe has stretched, which makes it appear much cooler. What happens? Yeah. How that CMB and the Big Bang theory can be linked or narrated. Example. The left one. This is the Earth. These are the planets: Earth, Moon, Venus, Mercury. There is a Sun, of course. With then Mars, This is at the cosmic background radiation. Do Big Bang has happened here at this point, where you can find the Milky Way galaxy. We are part of this nearby galaxies that the cosmic web like this, farthest visible quasars, or even Andromeda galaxy here, nearest galaxy to the Earth actually. Okay, this is the Lutena 76, one more celestial object, Proxima Centauri, one more star, nearest star, Luhan, Sirius is another nearest star, then Procyon, Pleiades, Vegas, Kepler, Actinus, Rosa, this is the formation of the wood cold from the earth actually. Okay, earth, this is the up to Neptune, Pluto, and this is the occurrence of the Halley comet 75 years responsible. What happens here? The CMB and the Big Bang theory goes in such a way. Before we are decoupling between these two, okay, the decoupling of the matter and the radiation, the universe was extremely dense and hot, and it was actually opaque to all radiation. After decoupling, it transitioned from an opaque to a transparent state that I told earlier. The residual radiation of that stage of the universe is what we call now as a CMB radiation. Yeah, this is what happens here in 1992, about 30 years back. A satellite named COPE, uh, background radiation, uh, cosmic background radiation experiment measured the CMB over the whole sky. Pope has established that the CMB is almost completely uniform wherever that whichever the direction you go from the Earth, with an almost constant temperature of about 2.7 degree Kelvin over the whole sky. But then the question arises that if the universe was so uniform, how were the different structures, such as stars and planets, were formed? See that how that different structures were formed. This is one question. The CMB radiation is not completely constant. If so, there were tiny fluctuations or ripples they can expect in the temperature phenomena at the level of just one part in about 100,000. CMB radiation is an evidence of the Big Bang origin of the universe. Even today, the investigation of the CMB radiation gives crucial insights to the beginning, expansion, and various occurring phenomena in the this. This is the description I mentioned. Only the cosmic microwave background radiation is an emission of uniform black body thermal energy coming from all parts of the sky. The radiation is isotropic, of course, whichever the direction you go, you'll get the same amount of the radiation to roughly one part in 10, 1 lakh. The root mean square variation is hardly about 18 microkelvin. After subtracting out of a dipole anisotropy from the Doppler shift of background, you will get this one. The later is caused, that is the dispersion is caused, peculiar velocity of the sun relative to the cosmic rust frame as it moves with a speed of about 370 meter per kilometer per second towards the constellation Leo, or maybe even with a galactic longitude, you can expect that what must be the variability. This CMB dipole and aberrations at higher multipoles have been measured consistent with the galactic motion. In the Big Bang model for the formation of the universe, inflationary cosmology predicts that only about 10 to the power of minus 13 seconds the nascent universe underwent, hardly this time, very short time, underwent exponential growth that smoothed out nearly all the irregularities. The remaining irregularities were caused by quantum fluctuations in the inflation field that caused the inflation event very long time. Remember here the time scale 10 to the power of minus 37 of a second, not even nano, not even pico, not even octave. Long before the formation of the stars and planets, the early universe was very small, much hotter, started about microsecond after the Big Bang, filled with a uniform glow, afterglow, what you can call, from its white hot fog of interesting plasma of electrons and baryons. These are the elements. As the universe expanded, no doubt, we are sure of it now, adiabatic cooling took place and the energy density of the plasma to decrease until it became favorable for electrons and protons to combine with protons, forming hydrogen atoms. This recombination event happened when the temperature was about 300 degree Kelvin, or when the universe was approximately about 400,000 years old at that time. As photons did not interact with these electrically neutral atoms, The farmer means earlier one, began to travel freely through space, resulting in decoupling of the matter. Because of this coupling, the cooler temperature of the ensemble decoupled photons has continued to diminish ever since. Now down to about a 2.726 plus or minus about 0.001 Kelvin. It will continue to drop as the universe in this. We are coming to very last slides. This is the panoramic view. Sorry for some scattered diagram actually. View of the entire near infrared sky, which reveals the distribution of galaxies beyond the Milky Way. This is the Milky Way galaxy. Image is derived from the 2ms mass extended source catalog. 1.5, it is almost 1.5 million galaxies it is holding. And the point source catalog, which can be of the order of about nearly 0.5 billion Milky Way galaxies. The galaxies are colored, sure. Color code is in such a way due to the redshift whether they are moving towards or away from that, or photometrically deduced from the K band. Blue are the one, blue are the one here, see the blue color wherever you can see that are the nearest sources of the size less than 0.01. Green are the moderate one, and red are almost distant sources, distant stars. Map is projected with an equal area of the galactic system. It's only for reference while you can't write. This is the last one. It looks like that. It is a logarithmic map of the observable universe. How was the, of course, earlier I showed the same case more or less. Observable universe in the sense, how far we can see that actually. This is how far see means this is what we are seeing from the cosmic microwave background radiation. From left to the right, if you go, spacecrafts and celestial bodies are arranged according to their proximity to the Earth. Is whichever the nearest to the Earth, low Earth orbit satellites, middle Earth orbit satellites, high Earth orbit satellites, communication satellites, then maybe the geostationary satellites, then to the extent of the moon, maybe some other things, maybe interplanetary missions, then interplanetary planets around us, then the sun, then Oort cloud, then after the Oort cloud, maybe the different stars of that kind. Here again a cloud actually. Then you can go for nearest star Alpha Centauri, or Ganymede, or Acta, Alpha B Centauri. Then this is the Milky Way galaxy part of it. Next nearest one is the Andromeda galaxy, or maybe the next galaxy is the cloud of that kind. Then we can go to the Big Bang. So stop here. This is the one, which is the last slide. How it is. A look into the past. Starting from T is here right now for the Earth. If you go back, the cosmic microwave background radiation was released 380,000 years after the Big Bang and serve as the background for all galaxies, which was helped. This dot was expanded like this. This expansion we are showing here is starburst galaxy of HF LS. The center is embedded in the cloud of the cold water vapor here, cold of the water vapor, and appears as it is about 880 million years after 880 million years after the Big Bang. Because of its low temperature, the water casts a dark shadow on microwave background. Detailed enlargement on the left it is shown here. Okay, yeah, this one, enlargement on the shaft. This represents a contrast about 10,000 fold expansion, stronger than its intrinsic variations of only 0.01%. Either light or dark spots, you can expect light or dark spots. This is what I say of the. You can zoom in the panel if you want actually to get a very good image. I will stop at this point actually. Even water which is formed not now either from the borewell or the ocean, it was formed about. People are saying that they don't use water. It's mainly because the contamination will happen from the container, the bottle, not from the water. Water will never get contaminated. Thank you. This is with the cosmic background radiations. If you are having any doubt, I would like